Welcome. Hello again. So this time we'll try to find bugs. Okay. So I will show you the emulator that I'm working on. Lately, I'm doing a blog post on my blog on my website. I'm releasing first the articles in Portuguese, but I'm translating it to English afterwards. So the last one I didn't have the time to translate, but I will show the current status of the project uh, and some issues that I'm having. Okay, and we will try to find them. Try to I don't know, uh, find ways to debug the emulator and and solve the issues. Ultimately, that is the goal. So, without further ado, let's share the screen. Yeah. Okay. Let me push the terminal. It will be Rust code. Okay. So first of all, let's go to my website and show you yeah, the series. So here we have the article talking about simulation, emulation, and virtualization, the difference between these terms and areas. And to complement, we start exploring emulators with the LC3 architecture, which is a really simple architecture based on the von Neumann architecture, which includes the input device, the the processing part, the memory, and the output device. Okay. Uh, and this explains what are instruction sets or HISA, and uh, we start to create developing the memory, the structure to hold the state of the registers of the CPU registers, and describe instructions and condition flags. And on the latest article which is the one that I didn't had the time to translate into English, I have the Portuguese version here. So we start implementing some instructions. Okay, so this is a really simple program. Okay, assembly program. This clears the R0 register. This creates a label, so we have the ability to reference the memory location of this label. This increments one on R0, so this is the destination part. This is the two operands. So R0 plus 1 and result goes into R0. This adds R0 with negative 10, so this makes a subtraction. So we don't need to have a sub operand, because a subtraction operand, because we can get to the same result with addition, right, using negative numbers. So the result goes into R1. This is a branch instruction, so when the last operation is 0, okay, is zero, sorry, is negative. Okay, n means negative. We loop or jump into loop. So, in other words, we go to the add instruction again. Okay, so why a negative 10? Because negative 10 is the target. Also, 10 is the target that I want. Okay, so if the target is 10, we can do a negative 10 subtraction with the current value of R0. So if the R0 value is less than 10, the result will be negative. So when the value is negative, we'll loop to that instruction again. And when the value of R0 reaches 10, 10 less 10 is 0. So this doesn't match, so we halt the program. Okay. Here we describe the composition of our instructions. Here we have an example. LC3 uses miss the name now. A fixed length instruction. That is the word. So the first 4 bytes identifies the operation. In this case 0001 means add instruction. The 3 following means the destination. So it's like an index. Okay. So 0 means R0, 1 means R1, 10 means R2, 11 means R3, so and so on. The next one is the source. Okay, so the source needs to be a register, and this means index as well. And this byte, this one, tells us if the following bytes are a value, okay, a scalar value. In this case, it is a 6, or if is an index to a register. Okay, so imagine that we are doing a multiplication by 2, we can put this byte, this black one, as 0, and here we should put 00011. So in this case, we would have R3 here. So if we had R3 with itself, R3, we are doing a multiplication by 2. Okay, and this is the way we do multiplications in LC3, because LC3 is so simple that we don't have complex opcodes like the multiplication or division and others. Okay, so this explains the fetch, decode, execute step. So the fetch is when we go to the memory, getting the next instruction. So this bunch of bytes up here, and we pass through the decoder, the CPU decoder, and on that decoder we know the instruction that we need to execute, and we go through the execution of that instruction on the execute phase. Okay, so up here we start creating some command line arguments to get the file, reading the file. Okay, we are converting the file into a vector. A vector of unsigned 8 bits, or a U8. We load the text into memory. Here is the memory structure. Sorry, put this in. So okay. And here's the main part of the emulator. So we create an emulator. We get the address, the base address, and here we load the binary that we read on the command line into the memory slot, okay, into this address, starting on this address. So up here we have this tag, okay, the origin tag. This means origin, of course, and this tell us where to load the binary. Okay, on this case, we are going to load the binary on this hexadecimal address. Okay, on this free 3000. Okay. Yeah. Now we have the fetching cycle. Okay. We have the default program counter value. Okay. So it's always 3000. Because the architecture tells us that. Okay? This is not an arbitrary value. We define our CPU structure with registries, and we initialize the structure, we initialize the program counter. We create methods to get the registers in the borrow manner. Okay, so we don't want to make a copy, no need to, and this creates the loop. Okay, and okay, this doesn't create a loop. The loop is created down here on the emulator, but this fetch the next instruction, okay, and moves the program counter along by 1, okay, incrementing program counter in 1. Okay, then we have the emulator, and on the emulator we have the execute methods when we execute the next instruction, and if the memory goes out of scope, we tell the user that, and we break the program because we don't want to panic the program, basically. Yeah. Then we have a list of all instructions that we have, additions, and so why those two, okay? Why we have two additions? Because we have that variant when we have the byte 5 flipped to 1 or 0. 0 meaning we are fetching data from a register, and 1 meaning is a immediate value or a scalar value. The same thing can be done with the AND. It follows the same structure. We have the branch, okay, so the branch is just one instruction. So on the assembly we will see VR hen, VRZ or VRP, but the instruction is the exact the same, is the instruction 0, okay, and the only thing that changes is the bits that we flipped 1, okay. So the bit 9 means positive, bit 10 0, bit 11 negative. Okay, and from byte 0 to byte 8 we have the offset. Okay, in relation to the program counter. Okay, in this case, saying that is in relation to the program counter, we are saying that is in relation to the VR, the break, okay? Because the program counter will be pointing to the VR at this moment. Okay, jump, all sorts of jumps, loads. Okay, this is used to load things in registry, memory address, relative memory address, absolute, and all that kind of stuff. Okay, yeah, stars, returns, trap. Trap is very important because trap allow us to do system calls, basically. Okay. We have the other instructions here. Yeah. So if you pay attention, these are contiguous. Okay, so we can simply uh, saying that 0 means break, 1 means head, 2 means load, okay? 3 means star. Um, we can make that kind of association. And the same thing for the registers. As I said before, the values that we have on the instruction are indexes. Okay, so 0 are 0, 1 are 1, 2 are 2, and so on until R7, which is our last general purpose registers, because we have other registers like the program counter that should not be directly manipulated by the user. So the architecture don't allow that. Okay. So here we have the next opcode. Uh, a method. Okay, so we are right shifting to 12 bits, so we stay with 4 bits. Okay, for and 2 6, so 60 bits, 16 bits. This gives us the raw instruction. This converts into an instruction enumeration. Yeah, here we match. Okay, so we will put here all the instructions. This is a sign extend. So sign extend allows to implement the two complements of a number. So basically we can pick a number with, for example, only 5 bits and convert it to 16 bits. Okay. So when the number is positive, is really straightforward. You just need to put zeros on the left side. But if we have a negative number, the last bit is used, or the first, depends how you are seeing the bytes. So that last bit must be flipped to 1, and that means the number is negative. So when for example, 5-bit number is negative, and we want to convert to a 16-bit number, we need to push the 1 and preserve the 1 as the first byte, and move the rest of the other part to the end of the sequence of bytes. Okay, so this implements a hand instruction. It seems complex, but it's really straightforward. So we write a shift 9 bytes, and we do a mask with 7. So okay, imagine. So imagine that you have, for example, I don't know, something like this. 001 1 let me see here to make something more meaningful. Okay, imagine that you want to is a add instructions, right? So let me open this on the other screen so I can copy. So the first four means an addition. So 1, 2, 3, 4 addition. Okay. The next three means the destination. Imagine that we want to implement addition between R0, R0, 5. Okay. So we want to add these two, R0 and 5, and store the resulting to R0. So this means R0, okay, source, this one, R0, right. We are computing against the immediate value, right? So 1, and the last 5 bits, okay, 1, 2, okay, 5 bits, we will put the value of 5, okay. Example, this is the value of 5, okay. 3, 4, 5. Right. I think it's right. Okay. So this is what is read. We don't have this separation, so this is a raw value. Okay, raw instruction. And we want to get the opcode. Okay, so to get the opcode, we pick this number, okay, and we do 12 right shift of 12 bytes. Okay, right shift of 12 bytes. So this means that we will discard 12 bytes. Okay. Okay. Since we are preserving the 16 bits, this means we got zeros on this part. Okay, but for simplicity, we will ignore that. Okay, so this means add. Okay, this is the add opcode. Now we want to get the destination. So the same thing. We discard 9 bits this time. Okay. So okay, we discard 9 bits. We get this value. Okay. But now we have the rest of the value. So we have the opcode here, and we want to discard that. How we can do that, this? So this is simple. We need to mask the number. How we do that? With a AND operation. Okay. So in this case, we need these 3 bits to be 1, or the first 3 bytes bits to be 1. Okay, and the number that means that is 7. Okay, because on binary 111 to hexadecimal means 7. Okay, same thing in decimal because it only shows after 9. Okay, so we need to do a mask with 7. This means that we will discard everything here and just stay with this number, and this means 0. Okay, and why this works? Because if we pick this value here and we do a mask with a bitwise hand operation with a mask 7, which means binary 111 and all zeros. Okay? And if you do a hand operation, we start to compute this, so 0, 0, 0, 0 and 0, 0, 0 and 0, 0, 1 and 0, 0, okay? Because this is Boolean logic, okay? It's Boolean algebra, so true, false, false and false, false, true and false, false, false and true, false, and true and true, true. Okay? So the same thing here, we have false, true, false, true, false, true, so 0, 0, 0. Okay? Same thing. So in fact, we as before, we got 16 bit number, so it is a lot of zeros until we get to 16, so we don't need that. Okay, let's do the same thing for our source. Okay, source 1. Okay, we pick this thing and we discard 6 bits on the right. So six bits on the right. Okay. And we do the exact same thing. We want just 3 bits, so we do a bitwise hand operation. And we stay with the last 3 bytes, okay, bits. 1, 2, 3. These means are 0. Okay? So I think this video will be a bit shorter than what I expected. No problem at all. Okay, this means RC. Okay, next part. We have a bit here, so we need to get a bit. So this means the mode of the operation. Okay. Just stop. Yeah. This means the operation mode. So we want to discard 5 bits. Okay. And now we just want to stay with just 1 bit, so we do a bitwise hand of just 1 bit. And we stay with this one. Okay? And 1 means that we are doing operation with a unit value. Okay, and the last thing is the value itself. Okay, we don't write discard anything because we are at the end, but we do a mask where the 5 first bits are up. Okay. And Now we do directly mask where we have 5 bits up. 4, 5, x, 1. Okay, we can check here if we are doing correctly. 1f. Okay. Great, 1f. So this means we want the first 5 bytes of this value. Okay. Everything goes away here. And if we pick this value and go to our friend Google and say, oh, look, we have a binary value. This we want hexadecimal value. So this means 5. And if we look to our instruction here, that means exactly that. Okay? So everything looks perfect. The only thing is this value needs to be extended sided value. Okay. Why that? Because the registries are 16-bit and this value is a 5-bit value. So we need to sign extend the value. In this case, it will be extremely easy, okay? Because it's a positive number. So all we need to do is make these 5 bits into 16 by adding zeros at the left. So 5 this. Okay, so really simple. Okay, now that we know how to extract the values, we can move forward. And this will be extremely simple now because we have done everything of this on our VS Code. So destination 9 to the left, mask of 7. Source 6 to the left, to the right, to the right, and mask of 7. 6 to the right, mask of 7. And we will check if it's a value. So this is a value. Okay. 5 to the left. Again, 5 to the right, and a mask of 1. Okay. 5 to the right, mask of 1. We compare against 1 if this 1 is an immediate value. So when this immediate value, we sign extended. So we pick the instruction and get the 5 first bits with a mask of 1f. Mask of 1f. Okay? And we say the original bit number. So we this way we can pick. We know how many bytes we need to add on the left. Okay, zeros, or check if the 5th bit is 1 and keep that 1 at the end of the 16 bit value to preserve the sign. And then we do, in this case, is an AND operation. So we do AND operation, bitwise AND with the source. Okay, we get a value of the register on the source. Imagine this is a AND. In this case, we all had to do a AND with the value stored on R0 and against the 5. Okay. And if it's not an immediate value, we get the values from the both registries, and we do an operation. Okay, yeah, really simple, right? So Y7 here and not 1F because if we go to here, when there's a source, we just want to get for 3 bits, which is the necessary to represent all the general purpose registers. Okay. So last one is method to update flags, because we need to update our flags on each instruction. So we pass a new value, and this picks a new value and check if the value is 0, and if it is, starts sets the flag 0 to true. If it is negative, store, or here we can see how we know the value is negative. So the 60 feet will be set as 1 if the value is negative, and otherwise it's positive. Okay. So this will execute, and the CPU module will tell us the next instruction. Okay, we implement just the first one. The next instruction is not implemented. Okay. So basically, is what this tells us. Okay. So next, I'm already writing the next one. It's also in Portuguese, but it's really easy to understand. So we have the addition. So this was the one that we have done here. So all the same thing, but instead of doing a hand operation, we do a sum. In this case, we are using wrapping heads, which is a function already given by Rust. Okay, this allows us to wrap around when we have the sign extent values. Okay, but we can also convert this into a bigger number. For example, U32. And sign that 32-bit value to the sum, and convert again into a U16 bit value. Okay, this is a branch. We implement the branch, the jump, return, jump, registry, load, load indirect, load base plus offset, load the effective addresses. Okay, bitwise not. Okay, to convert the bytes, encoding, store indirect, store register, and the trap. Okay, and the trap, we have this system calls available. We have the get C, which gets a character from the keyboard, but doesn't print on the screen. Okay, don't do a echo. And we have the output. This out prints the char stored on the R2, I believe, into the screen, and the puts prints the entire string until it gets to a null terminated value. In gets 1 char from the keyboard, but echoes the char back to the terminal. Sorry, I'm a bit slow today. And we have the puts p, which means the 16th value is split in 2 groups of 8 bits to store 2 characters on the 16th value. Okay, and this stops printing when the last 8 bits or the next first 8 parts of the bits are null. Okay? Which means 0. And we have the halt trap. And the alt makes the system halting, so it stops the execution of the CPU. On our emulator, we just stop the execution. On the real hardware, for example, on the x86, which is interrupt based machine, it means that hardware interrupts can wake up an altered machine. Okay, imagine that machine is halted, and we do a click, okay? A mouse click. That will trigger an interrupt, for example, and our machine can move away from a halt state if the interrupt handler or hierarchy has the logic to do that. Okay. Okay, but after that we have the memory addresses reserved to be used to store the status of keyboard, the screen, the machine, the data that we read from the keyboard, the data that needs to be written on the screen, and all that stuff. All of this code is to implement the get C, the outputs in inputs B, and halt system calls. And here is where I stopped writing the new article. Okay, so I have a lot more of new code added. But I think we can address that on another video. Maybe this afternoon. Yeah. So I have other things to do, unfortunately. So I will end the stream here. As usual, I will upload this into YouTube, so you can watch later, do questions, and yeah. And if you are into this stuff, please subscribe and leave a like. That is essential for me to continue to these videos. Yeah. So thanks once again for being here today, and see you.